Okay, so we are all back. Let's take a look at these questions together, and I would be great if we can take turns. The different breakout rooms can take turns to talk about what they discussed for that particular question. And don't worry, we'll work on it together. So it's okay if you feel like we're not so sure. That's totally fine too. Let's take a look at the first one. Here is asking us to choose a vector field from the first column below. So I think you either choose this first one or this one, right? They're very similar, and so it's also good for us to discuss. The first question is, if we were to do this line integral and around a small loop, would that be positive, negative, or zero? So any breakout rooms would like to share with us what they worked on for the first question?
Yeah, we don't have a problem.
Huh?
So we didn't,
yes. Okay.
right? The debate in our group was whether or not we could do this by hand or if we had to discuss this. So I'll just leave that open-ended for now. But what we came up with was that if we were to draw a circle, it would have to be either at the four corners of the square that encloses the vector field or any of the sides, so not at the origin. And if we look to see what is entering and what is leaving at any point on the circle, we concluded that the same moving in is the same moving out. Therefore, the dot product of f dot dr must be zero, right? And then another word or another way of thinking about it to just, I don't know, be confident in our answer was that, all right, what did we say? It's rotating. It's rotating counterclockwise.
Okay. So I think when you say rotating, you're hinting that this have something to do with the curl, right?
Correct.
Okay. And you say it is rotating. I think your natural conclusion for that, I think there is a non-zero curl. Is
right.
That right?
Yeah, that's the train of thought.
Product being zero. That seems like it's not going to match up with a non-zero curl, right? Okay, so very good. Thank you for sharing. Let's take a look at this together. So the first thing is actually to draw the loop to look at this integral. It's saying a simple closed positively oriented curve which does not go around the origin. So I know how to draw a simple curve. I know how to draw a closed one. What does positively oriented mean? What do you think?
So that your curve follows the direction of the vectors.
Okay. So when we have a loop, usually we by convention we mean counterclockwise to be a positive direction for the curve. So in this case, I'm gonna do a counterclockwise in terms of how I want to do the line integral. Okay. So this is my loop. It is simple, it is closed, it is positively oriented, and it's not at the origin. And let's look at how the line integral are going to add up. You can see on the bottom hand side, I draw my loop oriented in a certain way, so you can see the top and bottom leg of the loop is almost parallel with my vector. And the two sides of the loop is perpendicular to my vector. So I need to really think about just the top and the bottom leg when I do the integration. Do you agree? The dot product.
Yeah, because the components that are perpendicular to your vectors, when you dot it, they will cancel out.
Yes, very good. So the bottom one, you can see the vector is pushing to the left. My DL is to the right, so it gives me a negative value. My top one is a positive value. So in terms of the magnitude, the bottom one has a smaller vector field. The top one has a bigger vector field. So to add everything up, would you conclude that the F dot into dr or dl, I'm gonna say dr because the note said r, is it going to be zero or non-zero, larger than zero, smaller than zero, or zero? What do you think?
I think it's going to be positive,
zero.
greater than zero.
Yes.
Oh, no, yeah, greater than zero.
Yes. This one is breaking down into F for the top times DL on the top. So section 1 plus F on the bottom times DL on the bottom. And this one is larger than 0. This one is less than 0. But this larger than 0 has even a bigger magnitude. So overall, they add up to be larger than 0. So that is our first question is positive. Okay, the second one, will a paddle wheel spin if placed inside your loop? And if so, which way? Now, I think Nicholas has said earlier, it's going to spin, right? I think we all agree it is going to spin. So in which way would it spin, would you think?
Counterclockwise.
Counterclockwise, yes. So yes, the answer is yes, it will spin and in the counterclockwise direction. And counterclockwise of a spin is by convention a positive direction. And the line integral we calculated is also the positive direction, so they match up. That is why when we do the integral, they want you to choose a positively oriented loop just so that we can keep everything consistent. A third question, do you think the curl is 0 or non-zero inside the loop area?
It's non-zero.
Okay, because we have, very good, we have a paddle wheel. So if you look at this intuitively, you say it's non-zero. If you had looked at this conceptually by looking at the line integration, you also have the same results. It's non-zero, it's positive. And then now let's compute. So has any group got the chance to actually calculate the curl?
Yeah, we did.
Okay, so what is the result that you got?
We said it was positive 2K.
Okay, so just 1 second. So the first is negative y, I, x hat, j hat. Okay, positive 2k you said, right?
Yeah, that's right.
Okay, very good. We could do this real quick together just to, the rest of them, we don't have to do them one by one, but this one real quick. So you can see the x direction component is negative y. The y direction has x. There's no z direction, so the component for f is these, and you can calculate this. You will get 2k, and is in what direction? Sorry, 2k. Oh, k direction. Sorry. Yes. All right. So and again, it's positive. And the mathematically method give us the same results as our conceptual method as our intuition. So that is 3 different ways to do this, and we get it correct. Yes, we got it correct. Now, the next 4 question, as you can already see, it is getting us to do the divergence of something. So let's take a look at this together. Here, okay, this one is maybe a little bit confusing, but I'm just gonna throw it out there, see what you think. It's asking us to look at a surface. Okay, so this ds is a surface, and the surface, of course, you can write it using just say dA, which has a direction. But in this case, it is actually telling us the direction of the surface is sort of a normal vector pointing perpendicular to the loop that we draw. And to do this flux, to look at this flux, the f dot into dA, is the flux positive, negative, or 0? So if your group have already worked on the first vector A, very first one, would anybody like to share with us what they think answer to part E is?
It should be 0.
Should be 0. Okay, so can you say a little bit more about that? How do we know it's 0?
I didn't quite get to that, but divergence, you go for the I part, it's a y. For the x part, sorry. For the x part, you have a y down there, and when you take the derivative with respect to x, you get 0. And then
Okay.
same with the x part.
Very good. I see that you are actually using your answer to the mathematical answer to help you answer this particular question. That's totally valid. If you could simply just calculate it, I think by that method, you have already answered our question for number H. Okay, we can might as well do this, right? The divergence of F would be the X component with respect to X, Y component with respect to Y. It does not have a Z component, so I'm not gonna write it. X component is negative y. It does not depend on x, so 0. But the same way, likewise for x, dx dy is 0, so we get a 0. We get a 0 divergence. So now we want to be able to see our mathematical result actually match up this conceptually. Okay, this, you remember the method that we actually talked about in class? To look at this conceptually, we want to look at the flux of the vector field. So what they really mean by a n that's pointing away from the vector is, this is a closed surface, and you can see here this vector is actually 3D. It does not have variation in z, but it's actually filled up the whole space. So which means you cannot view this as just on a 2D surface. This thing is actually filled up and down. So we can look at our n hat is something pointing away from our vectors, which is perpendicular to the cross section. Okay, what we are looking at is a top view, and our n hat is pointing away from this cross section. That, if I may, is standing in this plane. What we are looking at is x and y. The n hat is perpendicular to this plane that my hand is trying to show here. I don't know if I can try to draw it a little bit better. If I'm going to draw a sort of a 3D view for my loop, if I could, it's going to be something like that. You can see it's like a volume, and I'm pointing away from that volume. So if there is a non-zero divergence, which means there is some source enclosed in this volume, that should be reflected by a non-zero flux going away from my surface. So by looking at this, you can see that the f is perpendicular to the n hat. My n hat is perpendicular. Nothing is actually leaving the surface. It is kind of curling up. So because f is perpendicular to n hat, when I do the dot product of f dot into dA, I get 0. So I get 0 flux. Okay? Which means the net flow outward would be 0 as well. There is nothing flowing out of the area. And that leads me to conclude the divergence would also be 0. Okay? I think this might be a little bit confusing, but if you wanted to look at this one, the next one would be a little more clear in terms of what do we mean by flowing out, flowing away from the center, or flowing into the center. Okay, so there are 1, 2, 3, 4, 5 more diagram left. For the next maybe 10 minutes or so. Now you have already familiar with this, maybe you can do it fairly quickly. I would want different groups, they take on different diagrams to begin working out. So let me take a quick look at how many breakout rooms we have. We have 12. So a breakout room 1, 2, 4. I want you guys to work on, let's label 1, 2, 3, 4, 5, and 6. So 1 to 4, I want you to work on number 2 first, then you have time, move on to the next one. Okay, so breakout room 1 to 4, work on number 2, 8 to 10. We actually have quite a lot. Let's work on number 3. And room 10 to 12, let's work on number 4. And if you have time, work on the rest of them. Start with one of them at least, so we can get people from that group to talk about what it looks like. Yeah, I think I only have 12 rooms. All right, so I'm going to again send you back to work on the rest of them. If your group happened to already work on the number I have assigned, simply just pick on the next one to start working on it. And as you come back, I will ask you to share your results with us. Again, you don't have to follow every step we go through in question 1. You think, I hope the process is now straightforward, is you first calculate this using mathematical interpretation. And then you look at this conceptually by either looking at the curl circulation or looking at the flux to see if the results are consistent with each other. So that is basically our method. So I'm going to go ahead and send you to the rooms for another about 10 minutes, maybe a little bit less than last time. And then we will bring everybody back to discuss. Before I send you off, are there any questions?
I have a quick question, actually. I was wondering, are we turning this in, or is this just like practice?
This is not for turning in, just for
Okay.
practice. Yeah.
Okay. All right. Thank you.
Professor, what about rooms 4 through 8? Somebody asked.
Oh, I forgot. Perfect. I don't have anybody to work on number 5. Look at me. Why don't you, for the 8, why don't you work on number 5?
Thank you.
Did I miss anybody?
No, there's a little bit of a repeat. So you want 1 through 4 to be working on 2, and then 8 through 10 to be working on 3. But you want 4 through 8 to be working on 5. So shouldn't it be 5 through 7?
Yes.
Okay.
All right. So yeah, so this will be room 11 to 12. Just to make sure that we all have someone to work on. I think you totally have time to work on more than one. Okay, I'm going to send you off, and I might jump in from one room to another, so don't be alarmed if I show up in your room. I'm simply there just to listen into the discussion. You don't have to stop and just go ahead and went along with your discussion, okay? Okay, I see Hunter and Chelsea, you don't have room assigned?
Oh, sorry. Yeah, my Zoom cut out, so I had to leave and come back in. I think I was with Janelle. It doesn't really matter which one I go to, but maybe room 2, I think.
12, you said?
2, maybe?
2?
Yeah, my Zoom cut out, so I had to leave and come back in. Sorry.
2. And Hunter, do you remember which one you were with?
No, I got into the meeting a little bit late.
Okay, so
Right.
we're working on the do you know which activity we're looking at?
We are the one that I'm looking at on screen right now.
Okay, yes, so that's the one. It also can be downloaded from Blackboard under the lecture notes and video folder, week 1. So I'm going to assign you to room 12 since they have only 3 people now, okay?
Okay.
Loop?
Yeah.
No, so our loop goes counterclockwise, right? So the top of the loop is going with the vectors.
Yeah.
And the bottom of the loop is going against the vectors. So the bottom of the loop they're still parallel, but they're anti-parallel. So the dot product is going to be negative. But because they're anti-parallel to the smaller vectors than the big ones, then when you add those two together, it's going to be a positive number. So it's going to be greater than 0, if that makes sense.
Yeah, I'm doing it right now. Dr. Ryan, they're just catching me up to speed. I'm just still trying to figure out why our top left column is positive and not 0.
The first diagram?
Yeah.
You're lucky. So we draw our C to be counterclockwise, right?
Yeah.
So which means that the top leg of our loop counterclockwise is pointing to the left, right?
Oh, that's right. That's right. I forget. Okay. Okay, right. And so what Juan was arguing was that of if we're drawing an infinite amount of circles that increases in magnitude going away from the origin, he's saying that the top of our loop is larger in magnitude. The component is larger in magnitude than the component of the bottom. And so when you add these things together, you have essentially a larger positive number and then a smaller negative number. And so that adds together to be a positive one, right?
He's also right. That's another reason. Let me share my screen with you. I could draw it a little bit better here. Okay, just 1 second.
Yeah, no, it looks like my point of confusion was how to draw a loop. I apologize.
So
Yeah, we're not the, yeah.
Let's say let's say our loop is not increasing as we go further, but equal magnitude, like this. Even if it's like this, it's still a non-zero curl, because when we draw a loop, if you wanted to directly orient your loop to be perfectly aligned with your vectors, so the loop will end up to be this donut shape, which will give you a larger leg on the top than the bottom. They still don't cancel out. But in this case, the one that's on the top is even bigger on top of a longer line. So it's still going to be non-zero. I didn't really talk about the details of the length of the loop because in here it's not necessary.
Okay. Okay, cool. No, that makes sense. I think I'm okay. Thanks, Dr. Ryan.
Sure. I'll jump to another one.
All right, so then let's go ahead and work.
The other one was pretty, it was pretty clear whether or not the top and bottom were going to be different.
Sure, yeah.
So I guess B would be no, it wouldn't spin.
Okay.
And then C is 0 because we kind of did it backwards.
And we calculated D already.
Yeah.
So for, I guess, E, the flow across the loop, if the loop's not at the origin, it's, I mean, even if it was at the origin, but it's kind of moving in just a little bit because the ones that are coming in are smaller and the ones that are coming out are bigger.
Yeah. Yeah, so it would have a divergence of, is it positive if it's more coming out? I forget now.
Oh, hey, Dr. Ryan.
Oh, hello.
For part E, we're working on number 2. We're wondering how, for E, they're still perpendicular, the F and the N, so it should go to 0, right? But
so part E, so in order to draw your, you're looking at the flux, right?
yes.
Okay, yes. So how we draw our loop and how do we look at our surface is decided by the shape and the direction of our field. So because you want to orient your surface to be either one side to be totally parallel, one side to be totally perpendicular. So our loop might be a little bit different than before. And let me share my screen with you so I can explain it by drawing it. So here, this is going away from the center. And if you wanted to look at the flux, you wanted to draw something that is either perpendicular to your you might call it r hat or whatever direction, the vector, or you want to draw it to be one side to be totally parallel to it. So in order for this to work out, you will end up with something that's looking like a donut shaped surface. Does that make sense? Because
Yes.
only for a donut-shaped surface to be either parallel to your vector or perpendicular to your vector on sides. So if you look at the flux here, now you can see that what is entering here, you have some vector entering and you have some leaving, right? And in this case, you will have more leaving than it is entering. You will have a non-zero flux. Does that make sense?
Yeah, that's like intuitively, that's what I was thinking. Like, there's more stuff coming out, speeding up through it. But how does that go with the integral up there? F dot n, when n is still perpendicular going through the page, doesn't that come out to 0? And then we have 0 times ds, which
F dot the n. In this case, F is parallel to n hat.
wait, where is n hat?
N hat.
Oh,
So our n hat actually didn't really change, is simply pointing away from the center, but our F changed. In this case, our F is curling around, and this in case our F is also pointing away.
okay. So I thought n was coming up through the page.
Right, that is why it's confusing. That's the wording of the question is confusing. We are looking at this. So we're looking at from the top view, and you can think of this as still has a depth, and we are looking at the perpendicular to the sort of a cylinder or thick donut here.
Oh, so it's like a surface, and n is going to be perpendicular to the surface at all of those points, right?
Yeah, yeah.
Okay, shoot. Thank you. Sorry about that.
No problem. How's everybody doing here? I see that you're all muted. Were you able to collaborate?
Yeah, we collaborated on the second one, working on the divergence and curl.
Okay, excellent. Any questions?
I think we were able to kind of work it out between ourselves for the most part.
Okay, very good. And we're about approaching time to bring everybody back anyway, so I will go ahead and leave you maybe a minute or so, and we'll come back, okay?
Thank you.
I have a question, Professor.
Go ahead.
Will the solutions be available for us to compare after class?
Yeah, I will post solutions for this.
Okay, cool. Thank you.
Okay. Okay, so as we all come back, let's spend some time to, hopefully we can get through maybe a couple of these together. Let's look at the second one. This one that is on the screen. My shared screen is gone. So let's look at this one right here. This one. Okay. So, by intuitively, conceptually, what do you think this field? Does this field have a non-zero divergence or zero divergence?
Non-zero?
A non-zero divergence, and why would that be?
Because it's radiating outward
It's radiating outward,
from the center.
and more importantly, it's divergent, but we talked about for a point particle, point charge. Actually, it will be a zero divergence anywhere except the origin. But what this one is different from that, it is also increasing in magnitude, right? As you go away. So if you draw sort of a donut-shaped surface to look at, whatever comes in, you have some coming in, you have some leaving, you have more flux leaving than the entering, give you a net flux of larger than zero, because whatever leaving is actually larger than zero. So here, by conceptually, we conclude the divergence of this field must be larger than zero just by looking at it. And we can calculate it, right? If you calculate, you get delta dot F equals dx dx, dy dy, and you get 2, which is indeed larger than 0, which is consistent with what we calculated. Now let's look at the curl. So for this one, do you think there is a zero curl or non-zero curl?
Zero.
Zero curl. So I think you can calculate it. That would be straightforward. But conceptually, would you be able to tell? And how would you tell that?
Yeah, if we use the paddle wheel method, at every point on that paddle wheel experiences not the same vector, but I don't know how to say it, but you guys know what I mean, right?
I think it was hard for me to do this the paddle wheel way because it's like I don't know if the x component of the obviously smaller arrow on the bottom of the wheel is not equal to the x component on the for the obviously bigger arrow on the top of the wheel because they're at different angles. So I had to do it mathematically for me to really convince myself that it was zero.
I think what Juan was saying was that for example, let's say you put a wheel in there and then the bottom side had a bigger X than the other side, but then it would cancel out because the Y would be bigger on the other side as opposed to the bottom side of the pinwheel if we were to put it in like that. So as X grows smaller, I mean the X component grows smaller, the Y will grow bigger, canceling out, making the pinwheel not spin.
Will you be able to share your screen with us to kind of draw on the whiteboard?
I do not have anything drawn. I kind of just said it. I'm kind of just saying it out of my mouth, but I didn't have anything drawn or any example on hand.
Yeah, I agree with you. The paddle wheel method is more difficult and it's less conclusive than the first one. So you can kind of think, okay, I put it here. Paddle wheel is not a perfectly, if you think of a circle, it's not going to be this particular shape, but I'm using this as an approximation. You can see that the two legs on the two sides are about equal strength pushing, and the top and bottom leg in this case, I oriented my paddle wheel to perpendicular, so it's not really pushing on the top and bottom leg. So in this case, it doesn't look like it's going to spin. But I agree with you, this is not as conclusive as first one. And that's why we always would want to have multiple methods to double check with one another to make sure. So in this case, the curl of this is actually zero. So let's look at another one. We will try to pick one from 3 and 4 and do another 5 and 6, one of them. So how about we do number 4? So anybody would like to share what they think about number 4 with the rest of us? In terms of divergence or curl, whichever you like to share.
Yeah, I kind of see one method or a loop that you could orient that would align itself with these vectors. It's in the top left corner of your diagram. There's about 4 vectors that can make a warped square.
You mean number 4?
Oh, I was looking at 3. Oh, geez. Okay.
Okay, 3 and 4 are the same. They just reverse directions.
Okay. Yeah, no. Okay, so we want, I'm so sorry. We want 4, right?
We want, it's okay, you can say 3. It's
sure. No, I mean, it's the same method I would take. I still see a number 3 in the top left corner, some makeshift square that you could make.
Like something like this?
Yeah, but I was thinking about connecting all 4 vectors. So the 2 below that square and then the 2 above.
Oh, like bigger, you mean?
That works. That works perfect.
Okay, so just a little bit bigger, right?
Yeah.
Okay. Okay, so what do I do with this loop then?
You would orient it with the directions of your vectors, so it'd be going clockwise.
Okay, so it doesn't matter what direction my vector is. When we choose a loop, we all.
Oh, that's right. We're looking for a positive orient. Okay.
Okay. All right. So what do we? Okay, and then from there, what do we do?
Well, you compare them to how they would look with your vectors. So right off the bat, the tops would, it looks like, cancel when you take the dot product, since those vectors would be perpendicular to your loop. Yeah. And the left and right would be the focus of the problem.
Yes, so we want to look at f dot into dl here and f dot into dl here. And f dot into dl on the left-hand side is negative because my loop is going down. My vector pointing up, so it's less than 0. This side is larger than 0. But which side is stronger in terms of magnitude?
It looks like the left side has larger magnitude.
Okay, so I will conclude that my f dot into dl loop overall, for this particular counterclockwise loop, I get a less than 0 value, right?
Right.
So it has a non-zero curl, which is less than 0. So anybody calculate the curl mathematically? Is it indeed less than 0?
Negative
yeah,
2k
we get
hat.
negative 2k hat, yes.
Negative 2k hat, excellent. So you can do this fairly quickly. So, okay, x plus y, y minus x and 0, negative 2k hat. And it's consistent, it is less than 0. Okay, so what about, so we've done the curl of this one. Why don't we do the divergence for number 4? So would you think there is a non-zero divergence for number 4?
No, it looks like it's going to be a negative divergence as well.
Yes, non-zero, which is negative, right? I think it's negative. Okay, so less than 0. So a non-zero divergence, which is negative, is suggesting that I have flux coming in, right? Does it look like I do have flux coming in?
Yeah.
Yeah.
Yeah. No.
There is more entering than there is leaving. They all actually, they're all entering. Everywhere in space, I can draw sort of this area. You can see here you are entering, here you are leaving, but whatever is entering is more than what is leaving. You give a net flux is negative. And when you calculate it, you can see plus negative x plus y over dy. You get negative 2. So it's consistent, which is indeed less than 0 that we did. Okay, so last one, I wanted to work on 6. I know I haven't assigned 6, but hopefully some of you had chance to look at 6. It's more interesting. So let's look at 6. First of all, let's look at the divergence. Do you think there is a 0 divergence or a non-zero divergence in the field?
I would say 0.
So let's do this, okay? The divergence of this field is dx, the x component, which is 0, dy, the y component, which is this, and indeed I got 0 because my my y component does not have an x dependence. Very good. So that is mathematically, and again, let's evaluate that by looking at the flux. So whatever is entering here, a little bit small and a little bit big, and a little bit small, a little bit big, whatever entering is the same as whatever goes out. So in and out are equal, give us 0 flux. I can look at elsewhere as well. So no matter where I look, I get a 0 divergence. So I would say, yes, the 0 divergence for all space for this field. What about curl?
There's 2 different curls. It spins counterclockwise on the left and clockwise on the right.
So put a paddle wheel here. Here is going to push it to spin this way. But I put a paddle wheel here, it's going to push it to spin this way. Okay, so it seems like a counterclockwise curl here, but a clockwise, so a larger than 0 curl here, a less than 0 curl here. And what about in the middle?
0.
It's actually 0 curl here. It's telling us the curl is different at different locations of the field, and we wanted to see if that is indeed true. We can try to confirm that with our math. 0 e negative x squared. So whatever left is going to be k hat d e to the power of negative x squared over dx, and that is negative 2x e negative x squared k hat. And you can see that it is dependent on x, right? At x equals 0, which is at the center, you got a 0 curl. And at x larger than 0, which is on the right-hand side, you got a negative curl, which is negative, as we see, consistent. And at x equals less than 0, which is on the left-hand side, we got a larger number. So that is consistent with as our conceptual indications. So that's all we're going to talk about for this activity. I will go ahead and bring us back to our class. Before we leave this activity, are there any questions?
Yeah, I do have a quick question. When
Go
we
ahead.
orient our loop, do we have to orient it along the field vectors?
So when you do
or
a
can we
loop,
just place it anywhere within the field?
to make the integration easier to calculate, you will choose a loop so that you can actually calculate your integration. So how do you make your integration calculate?
Got it.
Because
Okay.
you want your loop to be either parallel or perpendicular to your vector.
Okay, cool.
All right, thank you for the question. So we have done our activity. And again, using the curl theorem, we will be able to start with the integral format of Ampere's law and derive the differential format. So to remind ourselves, can you remind us, anybody remind us the integral format of Ampere's law? What is Ampere's law? It's about B, the magnetic field, right? So B dot into what?
DL
Yeah. Okay. Equals
equals
mu naught So what gives magnetic field? What produce a magnetic
It's a current.
Times current through. Yeah.
current enclosed? Excellent. So this is Ampere's law. And we're going to derive the differential format. So go ahead, and if you have a paper right beside you, go ahead and try to work on it. Give you a couple minutes. I won't send you off for groups, but just kind of take a piece of paper and try to work it out yourself. Okay, let's take a look at this together. I think that because we are asked to use curl theorem, right? Then the first step that we did is you simply treat this f vector as a b, which means I can write, sorry, this has to be just one integration over dl. So because we are using the curl theorem, sorry. The line integration of b dot into dl can be rewritten using the curl of b dot into d area. So the left-hand side. So do you guys get that part? Yes?
No, can you explain why those are equivalent?
Because I'm simply directly applying this theorem. This is telling me for any vectors, this form equal the left-hand side equals right-hand side. I'm simply replacing f with b now.
Okay, yeah, no, I see it.
Okay, so direct application of curl theorem on the left-hand side of your equation, and now you have your right-hand side. To further get rid of the integral, you see my left-hand side already in the integral format, but my right-hand side does not have an integration. So how do you continue to simplify? You need to be able to replace this with an integration, right? So
I would replace it with a double integral over current density.
Yes, very good. Who am I talking to? Hunter?
Yeah.
Oh, thank you, Hunter. Yes, I'm going to replace that with a current density. So current is defined as current density over dA. Do you remember that? What symbol do we use for current density?
Uppercase J.
Okay, and we call it what current density? This is a volume current density or surface current density?
Surface.
Currents all run on surface.
Wouldn't it be linear?
Can it be linear? Unfortunately, unlike the charges, which actually can live on a single line, our current has to run on the surface. And then you cannot integrate over, well, yes, you can integrate over a line, which is fine, but you would not call it a line current density. Does that make sense?
Mm-hmm.
We don't have a linear current density. We have a surface current density, we have a volume current density. We have only those two things. And this one is actually a volume current density. Despite you integrate over dA, this is called a volume current density. The surface current density is a K, and you integrate that over a line to get the current. Okay? Because current itself is already flowing in one dimension, that's why when you're integrating over the entire volume, you're integrating over area instead of volume. You don't integrate current over volume. It's not the same as the charge. That's the little confusing part. So the volume current density J dot into dA. Excellent. Now we look at the left-hand side and the right side of the equation that we do not have any special conditions for these surfaces. These are valid for any random surface and it's true for all surfaces. And therefore we can get rid of our integration sign to give us whatever we integrating it over must be equal. So curl of B equals mu naught J is the differential format of Ampere's law. And it's telling us that the J, just like how volume charge density give us the E field, the volume current density give us the B field. So there we go. We have our Gauss's law. This is Gauss's law. We have our Ampere's law. These are two of the Maxwell equations. And there are two other ones. That the divergence of B is equal to what?
0.
0. And why would that be?
Because magnetic fields do not diverge.
Yes, because magnetic fields always come in the north side and the south side. There is no magnetic monopoles. There's no one pole. And when you do divergence, it's always 0. Very good. So this is a no-name law. It doesn't have a name, or you can call it there is no magnetic monopoles. Unlike the E field, you can have a point charge. You cannot have a point magnetic point, right? And the next one is Faraday's law. Now Faraday's law is dB over dt, but when we are working with a static E field, which means it is not time dependent, this is 0. So if you're looking at static E field, you must be working with a E field that has a 0 curl. So let's look at this question before we go. Which one of these could be a static physical E field in a small region? I will go ahead and launch the poll for you. And please go ahead and enter your answer. Okay, so we got 43 out of 46 votes. Just a few more seconds. Let us finish the voting. Okay, so I'm going to go ahead and close the poll now. And let's take a look at our results together. We have majority voting for C. Only 2 can be a static physical E field. And the next popular answer is both of them for A. So let's take a look. Which one of these could be static? Now, before we have all these tools, and if we were given such a question, we might wonder, what does it mean? This could be a static physical E field. So what would be the physical constraint for the static E field? For something to be physical?
The point charge does not move.
Yes, static, very good. In the sense that it's not a time dependent, right? If charge starts moving, we may have current and we're dealing with the B field. And then that's not an E field, so that's yes, so indeed. But on top of that, it also has to be time independent. It doesn't change with respect to time. So for a static E field, yes, we need some static charges to produce the field. And at the same time, the curl of E has to be what?
0.
Has to be 0, yes. So these are our constraints for something to be a static physical E field in a small region. So for 1, would you think there is a non-zero curl, or yes or no? The curl of whatever field we're looking at is?
It's non-zero. It would turn clockwise.
Yeah, it would actually turn. So it's a non-zero curl, and it cannot be our static field. And this one doesn't. We actually worked on the curl of this in the previous class. So this one doesn't. So this one can be a static E field. Now my next question, sorry I went over time, is let's think real quick. What a kind of physical setup produced this 2? How can you produce 2?
A line of charges like in a parallel plate capacitor.
A line charge. I know a line charge give us the E field that's kind of in this. Now, if I'm talking about positive charges, it's like this, right? Infinite long line charge. Very good. So how do I produce something that looks like this? Like, where would I put my line charge? If I put my line charge here, and to be positive, you can see that as you go further away from the charge, should be decreasing instead of increasing. So I can't really produce this using a positive charged line. So what should I do instead?
A negative one on the left.
Yeah, making it negative on the left. Excellent. So I can simply just put a negative charge here, negative, negative. And you can see as you go closer, it's stronger. As you move further away, it is weaker. And you're pointing toward the negative, which will give us actually the field we're looking for in this particular region. Excellent. So answer is C, and we produce it with a negatively charged line charge. All right, so that's all for today. I won't see you on Friday. I will give you that time to do your pre-assessment in the Qualtrics. It's on Blackboard. And our first homework set will be available on Friday, and you can start working on it to be submitted in the week after, okay? All right. If you have any questions, feel free to shoot me an email, and I should be posting the office hours at the end of this week, okay? Goodbye, everybody.
Thank you, Dr. Ryan.
Thanks, Dr.
Thank you,
Ryan.
Dr. Professor.
Have a nice
Thank
day.
you.
Have a nice day, everybody.
Professor, I have a question.
Yeah, go ahead.
I took your class 2 years ago into
Okay.
2019,
Okay.
and I passed the activity portion of it.
Uh-huh.
But when I registered this semester for your class again, it wouldn't allow me because I already had taken the activity portion with the good grade.
Okay.
So I had it cleared by the department to
Uh-huh.
retake the class only. So I'm not in your activity.
Okay. Yes. So you don't have to attend the activity.
Oh,
Or and then in this semester, I'm not counting participation anyway.
okay.
You now, if you want, you can choose your old grading scheme where you use your original participation credit from the previous semester to do your grading for this semester. But I don't know how much of that advantage will give you.
Okay.
You might as well just choose our current grading scheme that does not have the activity session. And then you don't have to attend, but you're more than welcome to come, but you don't have to. And our grades are counted by pre-lectures, homeworks, and exams.
Okay. So for the activity, if I were to one day participate, is it the same link, Zoom link, as this course?
It's not, right, you're not in. How about I will email you the Zoom link for activity.
Okay, cool. Yes.
All right.
Thank you. Have a
Okay,
good
bye, Diego.